Let's take a look at special relativity and time travel. Time travel into the future, 100% possible. Time travel into the past, debatable, a subject for another video. The speed of light is 186,000 miles per second. It seems really quick, and from the perspective of the planets nearest us, it doesn't seem too bad. So there we are sitting on the Earth, and I'm not suggesting anyone does this, but we go and take a look at the sun. Now when we look at the sun, we're actually looking at the sun in the past. The light emitting from the sun takes 8 full minutes to hit the Earth. So whenever we look at the sun, we're looking back in time. We're seeing the sun as it was 8 minutes ago. Now again, let's increase that from a sun to another star we see in the sky. Remember, what we see at the sky at night are suns. We really can't see planets because the light hides them. From our perspective, our night sky is full of millions and billions of stars. In fact, more stars out there than grains of sand on the whole of planet Earth. You're looking through a telescope and you're watching this star. You're not seeing the star as it is today. You're seeing the star as it was 100 years ago. Let's stretch this out from the perspective of a star that happens to have a planet that is 65 million light years away. Let's say this planet over here is inhabited by a very intelligent species, and they've developed a device that is looking at the light from the Earth, and they can somehow turn it into a visual display, hypothetically. So the light from Earth has taken 65 million years to reach this device on their planet. If the device could create a view of what's going on Earth, they would see dinosaurs roaming the Earth. And it goes both ways. Again, we're studying the night sky, and we could be looking at a sun that just happens to have a planet. And we go and say, this planet looks like it could support life. You're looking at the planet as it was 65 million years ago. That planet may no longer exist. The sun may have gone supernova and destroyed that planet 1 million years ago. So again, you're looking at things that may no longer be there, and you're looking at them in the far, far distant past. I love SETI, and I have no issue listening out for radio signals from ET, intelligent life out there. Part of me goes, is it even worthwhile? What would it prove? Let's drop it back down to 100,000 light years. So again, we have a star and we have a planet. A species on that planet became intelligent and they started transmitting radio or television signals. Here we are today, sitting on Earth, and suddenly, eureka, we get a message from deep space. That radio signal is 100,000 years old. The people on this planet may have destroyed themselves with nuclear weapons, used up all their planet's resources, or again, the sun could have gone supernova and destroyed this life. We're listening to voices from way, way, way back in the past. And then people say maybe we can respond to them. Well, how's planet Earth doing in that respect? We've only had radio and television signals for about 100 years. We haven't even scratched the surface. Our signals have gone absolutely nowhere. Let's take a look at a couple of principles and try and do it in simple terms of relativity. Well, not all relativity, special relativity. General relativity would bring in gravity and a lot more complications. We're going to keep it simple, special relativity. One of the theories Einstein came up with first. One of the things we've got to get to grips with before we take this further is movement, and eventually you'll see time, is relative to the person viewing. So let's take one example. Here we have a grumpy spaceman sitting in space, and along comes a very happy looking spaceman. There he is. So from the perspective of our grumpy spaceman, happy spaceman is moving in space. This spaceman thinks he's stationary, and happy spaceman is actually moving. Now let's go and see it from the perspective of happy spaceman. Well, he's got the same view. As far as he's concerned, grumpy spaceman is actually flying past him. Well, who's right? It's all relative. They're both correct in how they see what's going on. Let's just take one last look at this. Now I've got both spacemen opposite each other. We've got grumpy spacemen and happy spacemen. Now from their perspective, now both of them are stationary. However, we're watching them from a spaceship, and from our perspective, they're not stationary. They're both moving through space together. That is seeing things from different perspectives. Now this is quite a radical idea to get the head around. What is strange, and Einstein proved this, is an event can happen simultaneously for one person, but another person will see the exact same event differently as an observer. Our spaceman has 2 torches on his backpack, and he has another spaceman in front of him. From the perspective of our spaceman, both light beams hit the green blocks at the same moment. So let's do that again. He turns on the torches at the same time, and both beams of light hit the green panels at the same time. And both astronauts 100% agree that's what happened. But let's put motion into the equation. Now, from our astronaut down here, he's viewing the same event, not a different event, the same event, but now the other astronaut is in motion. And what he will see is the one torch beam hit the green barrier first, and the second beam hit the barrier later. So how can this be fact? We know that from the perspective of the other astronaut, even though he's moving, he still sees it, that both beams hit the barriers at the same time. How can it be possible that 2 people can see the same event differently? Well, that's the radical thing about time dilation. Velocity, or speed. Just another recap. Everything is perspective to the person viewing it, and then we're going to say, is it relative? From your perspective, being the person down here, if you were to watch a motorbike traveling at 40 miles an hour, from your perspective, that bike is doing 40 miles an hour from the observer's perspective. However, if you're now on the blue bike watching the orange bike, from your perspective, the orange bike is only doing 20 miles an hour because you are in motion. I don't think there's anything difficult to understand about this. That kind of makes sense. Another example very similar to the spaceman is obviously they're both traveling together. As far as the blue bike is concerned, the orange bike is stationary. Now velocity, or should I say movement, is accumulative. Again, this seems so ridiculously simple. Our orange bike is now stationary and he throws a ball at 20 miles an hour. The blue bike thinks he can do better than that. He speeds up to 20 miles an hour on his bike and he throws the ball. Well, now the ball is traveling at 40 miles an hour. In other words, the speed of the ball, if you include the bike is in motion, the speeds are added together. Except where light is concerned. The speed of light is the same no matter whether it's observed from motion or standing still. So unlike the balls, if they were to turn on their headlights, even though the blue bike is in motion, the speed of light will remain the same. So if the speed of light is constant and remains the same, something else has to bend or give, and that's time. Let's take a look at time dilation. These are the thought experiments Einstein came up with. There's one with 2 bolts of lightning, and hopefully this is true, there was one where he envisaged himself on looking at the back of a train. So Einstein said, if I'm stood on the back of a train looking at a clock tower, and somehow, completely impossible, I could travel at the speed of light, viewing that clock tower, time would stop. So from Einstein's perspective, the clock doesn't move anymore, but back at the clock it is working quite normally, and that is the basis of time dilation. The faster you move through space, the slower you move through time. Another great example of showing how time dilation works is a light clock. Here we have a light clock in space, in a vacuum, and a beam of light is bouncing between 2 mirrors. Constant, no mechanical parts. Beautiful clock. Now, from the perspective of this astronaut, time is ticking away quite normally. However, we're now going to put one of these astronauts with the exact same clock in motion. The clock at the bottom, the light has to travel further. So it is taking more time to perform the same function. However, from the perspective of the astronaut, it's the same beam of light simply bouncing between the two mirrors. So one astronaut at rest sees one speed, and another astronaut, time has slowed down. The faster he goes, the more this effect kicks in. So again, it is simply a light beam bouncing between two mirrors because he is going so fast, time has really slowed down. The faster you move through space, the slower you move through time. A last example again of time dilation, where we have two rockets. One stays back on Earth, one takes off to a far distant star. As you can now see, the clock on the blue spaceship will run slower. When it arrives at its destination, it may be 2:30 on Earth, but it's only 1:15 on the ship. I guess it's all relative. How depressing it would be to be an astronaut that could actually do this. And here's my little thought experiment. If this spaceship took off and was 1 month into its journey, now remember this can't happen because of acceleration and g-forces, but he's 1 month into his journey, 50 years have passed on Earth. And in 50 years, they've developed a better rocket that goes much faster, so they send another astronaut. He's 1 month into his journey, and 50 more years has passed on Earth, and they develop an even better rocket. And they set that one off for the same destination. How depressing would it be as an astronaut that you take off and a future rocket overtakes you, and likewise an even later rocket overtakes you again? Time dilation and space travel. Here's some real examples. Now again, hypothetical. To get up to these speeds, we can't even imagine how we could build a spaceship or a spacecraft to get up to these speeds, but the maths behind it is real. So let's kick off very, very low initially. We're going to take only 10 light years. Remembering there's suns out there or stars out there that are 10 billion light years away. We managed to develop a ship that can go a quarter the speed of light. Probably realistic. 40 years it would take us to go 10 light years, and 38.72 years have passed on the ship. So already when that astronaut turns around and comes back, well, he'll be quite old, but he's gone 2.5 years into the future. Let's try it at 50%. So obviously 10 light years this time would only take 20 years on Earth. It has taken our astronaut only 17.32 years. So now we can see if he returned, he's 4.5 years in the future. So he is technically time traveled, not a lot. Quickly, we'll do 75% the speed of light, 13 years on Earth, 8 or 9 years on the ship. If we could go at 99% the speed of light, wow, I'll call it 10 years. So it's almost the speed of light, so only 10 years have passed on Earth because the star is, or planet is 10 light years away. 1.5 years have passed on the ship. Now that starts to get interesting. From the perspective of people on Earth, they think we've got a 20-year trip. We've got to go 10 years there, 10 years back. So we need to give the astronaut 20 years worth of food. Well, you wouldn't. You'd only have to give him 3 years worth of food because time will be different for him. 99%, even greater. 10 years on Earth, half a year. He's there and back in less than a year, but 10 years have passed on Earth. Let's move this from 10 to 100 light years, and let's go for even faster speeds. So to go 100 light years at 99% the speed, 101 years have passed on Earth, so everybody that you knew is dead, but only 14 years have passed for the astronaut. So he can get there and back in 29 years, but everyone he knew has long passed. 99.9% the speed of light, 100 years, 4.5. 99.99% the speed of light. 100 years, 1.5. And then the numbers start to get really crazy. Time dilation, the closer you get to the speed of light, really makes dramatic difference. 100 years have passed on Earth, half a year. 2 more examples. 100,000 light years at 99.999999% the speed of light. 14 years have passed for the astronaut. He turns around and comes back. So he's there and back in 30 years. And this is only for 100,000. Remembering there's planets there that are 9 billion light years away. And then I'm going to take it to one absolute crazy example. This example is obviously getting to the realms of lunacy. But let's do it. Somehow we can travel at 99.9999% the speed of light to a planet that is 100,000 light years away. Again, 100,000 years have passed on Earth, but amazingly, our astronaut could do this in 12 months. So he flies there, and he only needs 12 months worth of food and water. So he just needs enough water to survive only 12 months, 6 months there, 6 months back. So yes, time travel to the future is absolutely possible. But as a human race, will we ever do it? Well, it doesn't look like we can go far because there's no one to come back to tell us how successful it was. And again, we're barely traveling. 100,000 light years is nothing. So time travel is 100% possible. Will we ever be able to space travel to the stars? I doubt it.